Alright, so our first presentation was airplanes. And as you see, there's a lot more people in our group than most people's groups. So we had to do 2 presentations, so it was really difficult for us to figure out topics that would pertain to all of us. So we decided, we've all flown in planes before, so that's something we have in common, so why don't we do a project on that? And we decided to focus on the Boeing 747, which is a commercial jet, and then all the data would be the same.
And that was flying over an island in the Caribbean, St. Thomas, and because the island is so small, they have to put the runway so it backs right up to the beach so people will stand. That's people up to the fence that are getting blasted by the jet stream as it comes in.
Okay, so the history of flight. The first controlled and sustained and powered flight was on December 17, 1903 in Kitty Hawk, North Carolina by the Wright brothers. And the first passenger flight was on January 1st, 1914 between St. Petersburg and Tampa. The plane was piloted by Tony Jannus. And then the first flight of the Boeing 747 was on February 9, 1969. And then the dimensions of the Boeing 747. The wingspan is 211 feet and 5 inches, so like this seems from there to there. And then the length is 231 feet 10 inches, so the distance of the actual plane. And then the maximum takeoff weight is 875,000 pounds, and the plane can accommodate 460 passengers.
All right, so we started with the topic of flight, basing it off of Bernoulli's principle and some of the history behind him. Daniel Bernoulli was a scientist from Switzerland in the 1700s, and he was studying the conservation of energy. So during his experiments, he discovered that the velocity of a fluid, which is like water or air, as the velocity increases, the pressure of the fluid puts on an object decreases. And so, using Bernoulli's principle, since the air kind of works as a fluid, we have, so a wing of a plane is curved on the top, so that as air has to travel a larger distance to get to the other side of the wing, so this makes it move faster, which causes a lower pressure above the wing, and since it has less distance to travel underneath the wing, the pressure is higher, so it lifts the plane in a way. So the air pressure supports the plane. Yeah. And because of this, explains why planes can fly, and also why different wings have different shapes, such as like some wings they'll have like flaps that they can retract or use depending on how they're flying. So they'll be like on the surface of the plane, they'll have these little flaps that go up, which would cause more lift. All right, and one of the problems we wanted to solve was determining the acceleration of takeoff for this particular airplane. The average runway length at Minneapolis-St. Paul Airport is 3,190 meters. And then our initial velocity, we're not including the taxiing process, would be 0 meters per second. And then the final velocity needed to obtain flight is 80.556 meters per second. And using the formula of the total displacement, which equals the average velocity times the change in time, we were able to find a formula that we could use putting all these elements together. So initially we found, as you can see through the process, the final velocity plus the initial velocity over 2, which would be the average velocity. And then the change in time is the final velocity minus the initial velocity over the acceleration. And so going all the way through, we see that the acceleration needed for takeoff is 1.07 meters per second squared. Now surprisingly, this is really low considering the acceleration of gravity is 9.8 meters per second squared.
So now we wanted to figure out how you can maintain flight, and there are 4 things that are necessary for that. And they're lift and gravity, which oppose each other, and then that would, since they're opposing each other vertically, that you can plane stable. And then there's thrust and drag, which oppose each other horizontally, and thrust needs to overcome the drag to keep the plane moving forward.
So the first force is thrust, which is mechanical force, meaning that it is powered by an engine. The force of thrust moves the airplane through the air like to overcome drag, and it is a reaction of accelerating a mass of gas, which in order to do that, you pretty much just keep the gas up. And then the next force, lift, is obviously very important when it comes to flying an airplane. It opposes the weight of an aircraft, so it's going up. It's produced by a motion of an aircraft through the air, so the airplane is going this way and the lift is going this way. And then gravity, believe it or not, is important when it comes to flying an airplane. It is defined as the attraction that exists between any two masses. So in this case, it's the airplane and the earth. And it is needed to change the speed or direction of movement of an airplane. So without gravity, we wouldn't be able to turn our airplanes. And then according to Newton's first law, the force of gravity between two masses is the gravitational constant times the mass of the two objects divided by the distance between the centers squared. And then finally, drag, which opposes thrust, so it is going in the opposite direction of the plane. It resists movement, so drag is kind of it's like friction, it's holding the airplane back. It's created by air not moving smoothly across the surface, so that's why airplanes are kind of cone shaped, and it is aligned with the direction of the airflow.
So then we wanted to do, since when flying an airplane, unexpected things can happen, what the impact force of a duck hitting a plane would be. So if a plane is flying in the air and hits a duck, and the duck has a mass of 1/32 slugs, and a slug is a unit of mass of pounds per feet per second squared, which is a lot of units, so they just combine it into a slug.
And it's like 32 as well, so.
And so the change in velocity of the duck is 880 feet per second, and the change in t is 1/880 seconds. And this is just the formula of the average impact force. And then if you plug all that data into the equation on the previous slide, you get 24,200 pounds, and then that can be changed into tons, which would be 12.1 tons, or into newtons of 107,650 newtons.
So as you can see, the impact of a duck on a plane can be disastrous. In fact, over 140,000 birds have been hit by airplanes in the last 15 years. So it's important to calculate their damage to try to reduce the odds. Lately, it hasn't been as common because of the improved technology. And luckily, ducks don't really pose threats because after a certain height, they're flying out the same range, I guess.
So to wrap it all up, we talked about the history of flight, and then went on to talk about the dimensions of Boeing 747, and then we went on to explain the Bernoulli's principle, which was one of the main things we talked about to keep planes flying, and then we talked about the forces, thrust, lift, drag, gravity, and then we went on to figure out the takeoff velocity and the impact of the duck on the plane.
So these are shortcuts.
Okay, we can't slide, please.